When determining the appropriate size for a residential main breaker at the meter bank of a condominium complex, it is essential to account for the breaker's 80% rating. The 80% rating signifies that a breaker is designed to continuously carry only 80% of its nameplate amperage. For example, if a breaker is rated at 100 amps, it should not be subjected to a continuous load exceeding 80 amps. This design consideration is crucial for preventing overheating and potential failure of the breaker, as well as ensuring the overall safety and reliability of the electrical system. The National Electrical Code, or NEC, provides guidelines for calculating the demand load of a residential building, including condominium complexes. The demand load represents the maximum amount of electrical power that the building is expected to draw at any given time, taking into account factors such as the size of the units, the number of appliances, and the occupancy patterns. To accurately size the main breaker, it is necessary to perform a load calculation in accordance with the NEC. This calculation involves determining the total connected load of all the electrical equipment in the building and then applying appropriate demand factors to account for the fact that not all equipment will be operating simultaneously at full capacity. Once the demand load has been calculated, the next step is to determine the minimum acceptable size for the main breaker. This is done by dividing the demand load by 0.8, which represents the 80% rating of the breaker. The result of this calculation is the minimum amperage rating that the breaker must have in order to safely handle the expected load. In the specific example provided, the demand is stated to be 140 amps. To determine the appropriate size for the main breaker, divide 140 amps by 0.8. The result is 175 amps. This means that the main breaker should have a minimum rating of 175 amps in order to safely handle the expected load of 140 amps. If a 150 amp breaker were used, it would be undersized and would likely trip frequently, especially during periods of high demand. This could cause inconvenience and disruption for the residents of the condominium complex, as well as potentially damage the electrical equipment. In addition to considering the 80% rating of the breaker, it is also important to select a breaker that is appropriately sized for the conductor that is feeding it. The conductor must be able to safely carry the amount of current that the breaker is rated for. The NEC provides tables that specify the minimum allowable ampacity for conductors of different sizes and materials. When selecting a conductor, it is important to consult these tables and ensure that the conductor is adequately sized for the breaker that it is serving. Furthermore, it is crucial to take into account any applicable local codes or regulations that may impose additional requirements for electrical installations in condominium complexes. These codes may specify minimum breaker sizes, conductor sizes, or other requirements that must be followed. It is always best to consult with a qualified electrician or electrical engineer to ensure that the electrical system is designed and installed in accordance with all applicable codes and regulations. In summary, when sizing a residential main breaker at the meter bank for a condominium complex, it is essential to consider the 80% rating of the breaker. Divide the calculated demand load by 0.8 to determine the minimum acceptable size for the breaker. In the example provided, with a demand of 140 amps, the main breaker should be sized at 175 amps. It is also important to select a breaker that is appropriately sized for the conductor that is feeding it, and to comply with all applicable local codes and regulations. Accurately sizing a main breaker involves several steps, starting with a thorough calculation of the total demand load. This calculation should not only include the general lighting and appliance loads of each individual condo unit, but also factor in common area loads like hallway lighting, elevators if applicable, and any shared amenities such as swimming pools, gyms, or laundry rooms. The NEC provides specific guidelines and tables to assist in determining these demand factors, taking into account the diversity of use and the likelihood of simultaneous operation. It is important to understand that the demand load is not simply the sum of all connected loads, but rather a more realistic estimate of the maximum power likely to be drawn at any given time. The 80% rule is a crucial safety factor designed to prevent breakers from overheating and potentially causing fires. Circuit breakers are electromechanical devices that interrupt the flow of current when it exceeds a predetermined level. This interruption is achieved through a thermal or magnetic mechanism that responds to the heat generated by the current passing through the breaker. When a breaker is continuously loaded near its maximum rating, the heat generated can cause the internal components to degrade over time, leading to premature failure or even a fire hazard. The 80% rule mandates that the continuous load on a breaker should not exceed 80% of its rated capacity, providing a safety margin that allows the breaker to operate within its design parameters and dissipate heat effectively. This rule is particularly important for main breakers, which are responsible for protecting the entire electrical system of a building. For a condo complex, the main breaker must be sized to handle the combined load of all the individual units, as well as any common area loads. If the main breaker is undersized, it will trip frequently, causing power outages and potentially damaging equipment. If it is oversized, it may not provide adequate protection against overloads and short circuits, increasing the risk of fire or electrical shock. In the example given, a demand of 140 amps necessitates a breaker with a minimum rating of 175 amps as calculated by dividing 140 by 0.8. However, it is important to note that breakers are typically available in standard sizes, such as 150 amps, 175 amps, 200 amps, and so on. In this case, a 150 amp breaker would be insufficient, as it would be overloaded by the 140 amp demand. Therefore, the next larger standard size, which is 175 amps, should be selected. It is also essential to consider the ampacity of the conductors feeding the main breaker. The conductors must be sized to carry at least the rating of the breaker, and in some cases, they may need to be larger depending on the installation conditions and the type of conductor used. The NEC provides tables that specify the allowable ampacity of different types of conductors based on their size, insulation, and temperature rating. These tables should be consulted to ensure that the conductors are adequately sized for the load they will be carrying. Furthermore, it is important to consider the voltage drop in the conductors. Voltage drop occurs when the voltage at the end of a conductor is lower than the voltage at the source due to the resistance of the conductor. Excessive voltage drop can cause appliances to operate inefficiently or even fail prematurely. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, conductors should be as short as possible and should be sized appropriately for the load they will be carrying. In addition to the NEC, local codes and regulations may also impose specific requirements for electrical installations in condo complexes. These requirements may vary depending on the jurisdiction and may address issues such as the type of wiring allowed, the location of electrical panels, and the requirements for grounding and bonding. It is important to consult with the local authorities to ensure that the electrical installation complies with all applicable codes and regulations. Proper grounding and bonding are essential for safety in any electrical system. Grounding provides a path for fault current to flow back to the source, allowing the circuit breaker to trip and energize the circuit in the event of a ground fault. Bonding ensures that all metal parts of the electrical system are electrically connected, preventing voltage differences that could create a shock hazard. The NEC provides detailed requirements for grounding and bonding, including the size and type of grounding conductors, the methods for connecting grounding electrodes, and the requirements for bonding metal enclosures and equipment. It is important to follow these requirements carefully to ensure that the electrical system is properly grounded and bonded. In summary, sizing a residential main breaker for a condo complex requires careful consideration of several factors, including the demand load, the 80% rule, the ampacity of the conductors, the voltage drop, and the applicable codes and regulations. By following these guidelines, it is possible to ensure that the electrical system is safe, reliable, and efficient. Always consult with a qualified electrician or electrical engineer to ensure that the electrical installation is designed and installed in accordance with all applicable codes and regulations. The process of determining the correct size of a main breaker goes beyond a simple calculation. It necessitates a comprehensive understanding of electrical principles, safety standards, and the specific requirements of the installation. Firstly, the load calculation must be meticulously performed, accounting for all possible electrical demands within the condominium complex. This involves not only the individual unit loads but also the communal loads such as lighting, elevators, and other shared facilities. The NEC provides detailed methodologies for this calculation, employing demand factors that reflect realistic usage patterns rather than simply summing up all connected loads. Secondly, the 80% rule acts as a critical safety margin, ensuring that the breaker operates within its design thermal limits. Continuous operation at or near the breaker's rated capacity can lead to overheating, degradation of internal components, and ultimately, a higher risk of failure or fire. By limiting the continuous load to 80% of the breaker's rating, this rule helps to prevent such hazards and ensures the long-term reliability of the electrical system. Thirdly, the selection of appropriately sized conductors is paramount. The conductors must be capable of carrying the full rated current of the breaker, and in some cases may need to be oversized to account for factors such as ambient temperature and conductor bundling. The NEC provides tables that specify the allowable ampacity of different types of conductors, and these tables must be consulted to ensure that the conductors are adequately sized for the application. Fourthly, voltage drop must be carefully considered. Excessive voltage drop can lead to inefficient operation of electrical equipment, reduced lighting output, and even premature failure of motors and other appliances. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders, and conductors must be sized appropriately to meet these limits. Fifthly, compliance with all applicable local codes and regulations is essential. These codes may impose additional requirements beyond those specified in the NEC, and it is the responsibility of the electrical contractor to ensure that the installation meets all applicable standards. Sixthly, proper grounding and bonding are crucial for safety. Grounding provides a path for fault current to flow back to the source, allowing the breaker to trip and to energize the circuit in the event of a ground fault. Bonding ensures that all metal parts of the electrical system are electrically connected, preventing voltage differences that could create a shock hazard. In the specific example provided, a demand of 140 amps necessitates a breaker with a minimum rating of 175 amps, as calculated by dividing 140 by 0.8. However, it is important to select the next standard size breaker available, which in this case would be 175 amps. A 150 amp breaker would be insufficient and would likely trip frequently, while a breaker larger than 175 amps might not provide adequate protection against overloads and short circuits. It is also important to consider the available fault current at the location of the main breaker. The fault current is the amount of current that would flow in the event of a short circuit, and the breaker must have a sufficient interrupting rating to safely interrupt this current. The interrupting rating is the maximum amount of current that the breaker can safely interrupt without being damaged. The fault current can be calculated using various methods, including using a fault current calculator or consulting with the local utility company. It is important to ensure that the breaker's interrupting rating is greater than the available fault current. In addition to the above considerations, it is also important to consider the future expansion of the electrical system. If there is a possibility that the electrical demand will increase in the future, it may be wise to install a larger breaker and conductors than are currently required. This will allow the electrical system to be expanded without having to replace the main breaker and conductors. Finally, it is important to document all of the calculations and decisions made during the sizing of the main breaker. This documentation should include the load calculation, the voltage drop calculation, the fault current calculation, and the selection of the breaker and conductors. This documentation will be helpful for future maintenance and troubleshooting of the electrical system. The selection of a 175 amp breaker in this scenario is not merely a matter of exceeding the calculated demand, it's about ensuring the entire electrical infrastructure operates safely, reliably, and in compliance with established codes and standards. The intricacies of electrical sizing extend beyond the basic mathematical formula, demanding a holistic understanding of the system's components and their interactions.